Welcome back to Quite Basic Math. We will continue where we stopped last lesson, and we said we're introducing QBM 101, which starts with a fundamental topic titled set theory. We'll be looking at how we identify elements one after the other and some set definitions that would be used or be referred to as we go on in this lesson. Right, the first thing is you want to define what each term means. What do you understand by set theory? You know what a theory means. It talks about you having to define assumptions made or laws made that guide a particular definition. And a set is just collection of items. All right. So if I have a set, I would say a set of bags. You have bags put together in a particular place. All right. A set of books. So it just simply talks about the collection of items. Alright, that's what we understand by set. Alright, so if I say a set of sort of books, it could be academic books, financial books. All the points means that we are collecting types of books together and putting them in a certain column, bounded. Okay, there's an important term that comes with our definition of set. We don't just collect items, we also put them in a place where they are bounded. So if I say a set of books, it is not yet a set until those books are kept in a place where boundaries are put in place. Alright, so if I define a set A, one thing you must take note of is when we are defining sets, we use capital letters. Alright, so if I say a set A, it's important that I am using a capital letter A to define that set. Alright, so let's say set A is the alphabet, the English alphabet, okay, and we use the symbol, this curly bracket, to define where our set will be placed. Alright, so if I say English alphabet, alright, if I say English alphabet, let's define a set English alphabet, okay. We are taking it step by step. Alright, so what we have here is a set of English alphabet. And if I'm going to list these items, if I'm going to collect them, you know what English alphabet is. It starts with A, B, C, D, and so on and so forth, up until the final letter Z. Okay. Now it's important that you take note of some things. In set theory, we do not repeat items. No repetition is allowed. We do not repeat items. However, in a case where items are repeated, you must take note of the fact that the items that are repeated are not counted. Okay, so if I'm going to look at the number of items I have in this set A, which we call the cardinality of the set. So if I say n of A, which means the cardinality of set A, this means the cardinality of set A. Okay, this means the cardinality of set A. Now let me quickly define that, since we are defining terms. Now the cardinality of a set is simply the number of elements in that set. So if I have n of A, which means the cardinality of set A, in this case I'll have 26, I believe. We know that we have 26 English alphabets, but mind you, if somebody writes A, A, probably because he loves the letter A in this set, now this might look aesthetically nice, but the point is I wouldn't count letter A twice. Letter A is letter A, so in set no repetition is allowed. So which means that although you might, just to test your understanding, someone can be mischievous to give you a set as has repeated items. It doesn't mean that you now have repetition in your counting. So you would still count A as just a single A. Alright, so which reduces our cardinality of set A to be 26. Alright, I hope you're learning. Then what else do you need to know? You need to know some classes of sets, or what you call forms or types of sets. Now your set could be let's look at some basic type. You could have finite classification in terms of numbers, in terms of cardinality. You could have finite set or infinite set. Alright, now if a set is said to be finite, from the word finite you have an idea. Alright, so what this just means in terms of cardinality, it means that number of elements in that set, let's say set S, okay, number of elements in set S is countable, meaning that it's an element. Do I put this now? Okay, it is not equals to infinity. Yeah, this is important. This is important because it goes beyond saying countable and uncountable. There are some sets that are not countable but yet are finite. Okay, so important that there are some sets rather that are that are countable are uncountable but yet finite. Yes, some sets are uncountable but yet finite. So it's important that you understand that the idea is, if the cardinality of your set is not equal to infinity, then you have a finite set. But if the cardinality of your set is infinity, okay, that means that you have an infinite set. So you can see various examples. For example, if I say a set S is defined as all even numbers, okay, I don't even need to say all even. If I say even numbers, what do you begin? What do you begin to count? You start to count. You could say 4, you could say 6, you could say 2, you could say 8. It goes on. It's an endless list of even numbers. So in that case, we have an infinite set. For a finite set, a good example is the English alphabet, because you definitely know the cardinality. So if I'm going to if I'm going to give a formal definition of what a finite set is, I will just simply say that a finite set, okay, a finite set is a set of known cardinality, basically a set of known cardinality. So if you know the cardinality of a set, you already have a finite set. Okay, and what happens to an infinite set? Of course, on the flip side of it, an infinite set is a set of unknown cardinality. You don't exactly know what the cardinality is. All right. Now we could also have various kinds of sets beyond its cardinality. You could also have a set based on, you could also have a set based on the content and what you have in the set itself. You could have something called a null set. All right. You could have something called a null set, although this is still based on cardinality, because a null set is still also regarded as an empty set. So what happens when you say a set is empty? Now this is very, very important. A set is said to be empty if it has no elements, basically. So meaning that the cardinality of such set is equal to 0. Alright, so if the cardinality of a set is 0, it means that the set is empty or it is a null set. And there is a way we represent a null set, okay? If we say a set A, a set S, let's say I like the letter S, let's use the letter S. So a set S is said to be empty. A set S is said to be empty if, okay, if n of s equals to 0, right? And it is represented, okay, by the symbol. Now this is very important, by the symbol phi. Now if you say phi, we understand that you're talking about an empty set, or you put a curly bracket with nothing inside. Either one of these could represent an empty set, but you can't use the two together. What do I mean? Now look at this. I can't define an empty set. This is not an empty set, okay? Null set is not equals to this. This is not an empty set. Now a lot of people make this mistake a lot. You're trying to define an empty set. You either use the symbol phi, right? Or you use this curly bracket with nothing inside. If you do this, if you write the curly bracket and then put in phi in this is actually a unit set. All right. What does a unit set mean? This is a unit set. A unit set simply is a set that has a cardinality of 1. That is, you just have one element in the set. This is no longer null. So for it to be null, you either just use the symbols phi, or you write a curly bracket, okay, with nothing inside. I hope we are learning. Okay. What else do we need to know about sets? Basic notation is this symbol here. All right. So if I say that, let's say x denotes let's say x denotes an element of a set. Now, one important thing you must take note of is that just like English is a language, so is mathematics. All right. So sometimes we do not like to use words. We want to use symbols to communicate a message. Imagine you have to say so many things mathematically, and you don't want to be putting it in words. That would be ambiguous and permit me to say unprofessional as a mathematician or as a mathematics person. All right, so it's important that we put these things in symbols, in equations, in ways that we can be able to put them down. Right. So for example, if I say x denotes an element of a set, I can write it this way: x using this symbol, e, then let's say set A and A. So this simply means anybody that sees this will understand that x is an element of A. If I slash it, I'm sure you know what that means. X is not an element of A. So it's important that we know these things. Let's quickly track back to what we have been learning to see what we are talking about here. So look at this set. We said A denotes the set of English alphabets, A, B, C, D up to Z. So if I then take a letter A, for example, I can say small letter A is an element of capital letter A. Everybody understand what I mean now, right? A is an element of A, right? And what if I say 1? Number 1 is not an element of A. Alright, so that is symbol. What else do we need to learn here? Okay, so let's also look at some interesting things about a set. Now we could also talk about yes, I said n of s equals to 1 denotes a unit set. Is that not so? So another name for unit set, okay, is singleton. Singleton. We call it singleton too. Alright, so if I say a singleton or a unit set or a singleton set, however way, it simply means that a set with a cardinality of 1. You just have one element in that set. Alright. Now, if you also have operations, you could also carry out operations given different sets. Alright, so some of the operations that we have in a set operations, okay. So operations on set. Some people call it set of algebra, however way it goes. Okay, those are just notations. The first one is union of sets. All right, union. Let's start with something basic. Union of two sets. All right. So if I have given set A and B, all right, the union is denoted as okay, is denoted as or by denoted by A union B. Okay, so this is the symbol for union. It's just like a capital U. Okay, capital U. A union B simply means, now what does it mean? Now this means, from the word union, you have an idea of what it means. Union, the coming together of two sets. But it is more than just coming together of two sets. You don't just bring them together, you actually see that all the elements in set A and B are put together. All right, we are not in any way having to check if they have anything in common. We don't care. Even if they have anything in common, the point is bring everybody in A and everybody in B together. So set A union B is the coming together of set A and B such that everybody in A and everybody in B are found together. All right, so B, the second one is intersection of two sets. Now it could cut across three sets. Okay, it could be four sets. The point is every set element is now found in their union. Okay, each and every set, and the ones that intersect, or the ones that are not even found. For example, if you have an element in A that is not in B, you don't care. Union brings everybody together, and that is why some people say that this set A union B is actually the elements in this set, or some people say and or the elements in this set. We'll see that in De Morgan's theorem, but let's take it a step at a time. Now intersection, let's see, for intersection is denoted with this letter, more like an inverted U. All right, an inverted capital U, or maybe an N, a strange N. I don't see this as an N though, but let me just say an inverted U. All right, so it is denoted by A intersection B. Now what does this mean? This is quite similar to the union of two sets. What you are doing here is you are bringing the elements in this set together, but you are looping through to ensure that you have the elements that are in common alone. So you are only collecting the items of the elements that are common to both set A and B. Take note, unlike union that just brings everyone together, all right, for intersection, you are only considering those elements that are in common. That's where the word intersection comes from. Intersection is used a lot in algebra, apart from geometry. You could also use intersection in the case where you have two lines. You could be asked to find the point of intersection of two lines, right? And in that case, the point of intersection of two lines is simply the solution of solving two linear equations simultaneously, basically. So you're just looking for the point where they have something in common, which is basically solving the two equations. Alright, that's by the way. You could check my previous videos on equations to know what I'm talking about there. Alright, so you would see how we solve two simultaneous equations in different forms. Two simultaneous equations, or we solve simultaneous equations having two variables, alright, or two unknowns. Okay, Now moving on, let's see some basic examples to pinpoint what we've been saying. Alright, so let me define two sets for you. Let's assume, because we are defining sets basically before we begin to define them on intervals. I mean, begin to define them, setting boundaries and much more technical terms. But let me define a simple set for you. Now, if you have a set A, I'm not supposed to do this though because this is already advanced algebra. Okay. Alright, but I will do that for the sake of those that have very rusty mathematics foundation. Okay, so look at this. If I say a set A equals to A, B, C, D, okay, and I say that a set B equals to, let's say, C, D, E. Now, having these two sets you have here, right? If I am going to take the union of these two sets, it simply means that I'm bringing everything in A and everything in B all together. So I'll just have A, B, C, D, E. I believe you got that, right? So this is the union of the sets. Mind you, C was actually intersecting here. Likewise, D. I didn't repeat it, so it's important that you take note of that. So the cardinality of the union of the set is actually 5. All right. Okay. Now moving on. If I have A intersection B, how do I operate these sets? So you look at set A and set B. What do they have in common? I believe C and D. Okay. So C, D, where the intersection, the cardinality of the intersection is 2. So A intersection B is C, D. So I believe this example has pinpointed the operations, the basic operations on sets. So if you ask to evaluate the union of two sets, you know what they are saying, and the intersection, you know what they are saying. They might not ask you to evaluate, but they might ask you to explain or prove some given sets, but you understand their basic idea behind proving these sets. Okay, let's go a step further. Now let's look at some other operations you can find in a set. Look at complement of a set. Let's look at the complement of a set. Okay, now the complement of a set is quite interesting. Why? You can denote it by A prime or A with actually the C, but superscript C, where the superscript C represents complement. You get it? So either one of it is fine. If you say A prime or A complement, they both represent the complement of set A. Now what does this mean? Now the complement of a set is simply the element found, let's say X is an element of A. Now I'm going somewhere. Let's assume X is an element of A, alright? So its complement, A complement, is simply saying that I want all the elements in the universal set. Okay, I didn't talk about this. Now let me quickly talk about universal set. Now whenever you have U like this or whatever way it is represented, the universal set is simply the set of all sets. I come again. The universal set is also called the mother set. It actually gave birth to the rest of the sets. Okay, so the mother set or universal set is the set that contains every other set. Okay, the set that, for example, if I say that I have a set A that is vowel letters, okay, and if I have a set B that contains consonant letters, okay. Now what this means is that the universal set here is going to be, let's say, universal set. What do you think the universal set will be? If I'm saying alphabets, right, and I mentioned vowel and consonant, you agree with me that the coming together of the two, or looking at it holistically, will leave my mother set being the English alphabet. Okay, actually, so the English alphabet will contain both the consonant and your vowel alphabets or letters. Okay, so your universal set or mother set is the set of every other set, a set that contains all the other sets. So if I'm going to be taking the complement of a set, what it simply means is that I will look at every other element in the universal set, but not in the element A. So the negative here is the difference of two sets, and I will look at that in the next. Look at that next. Okay, but then you need to first understand what is going on here. Now the universal set you understand, the set A you understand. So its complement is the elements in the universal set that are not found in A. So what about B complements? The elements in the universal set but not found in B. So the point is, you must understand that there is a universal set that houses every other set or every other element, But once I take the complement of a particular set, I'm interested in every other element in the universal set or in the full set, but not in B. It's very important, but not in B. So likewise, C complement, what do you think that would be? Of course, all your elements in the universal set, but not in C. So let's now see what these symbols mean. Let's see what this negative means. Let's quickly look at the difference of two sets. Difference of two sets, okay? Difference of two sets. So if I have two sets and I take the difference of the set, what it simply means is, I'm sure you can have an idea from what I said here. Now, if I say A complement is universal set minus A, it simply means that, and I said universal set minus A means all the elements in universal set but not in A. So that's what difference of two sets means. So if I say A minus B, this actually means all the elements in A but not in B. It's actually denoted as A intersection B prime. I guess it's getting a little twisted here, right? But you get to understand what I'm saying. If I say A minus C, this means that all the elements in A but not in C. Okay, so this is the difference of two sets. Let me quickly give us an example. Let's just go back to that example we used. So look at A and look at B. If I'm supposed to have the difference of A and B, okay, A minus B will be what? You look at A, you're looking at all the elements in A but not in what? But not in B. So what would you do? You will look at A and write everything you have in A, but anyone that intersects with B, you eliminate it. So it's like saying A minus B. Look at A, take every part of B that is in A and write every other thing in A. So A minus B, I take that again. Look at A, take everything that is found in B in A and write everything else that is left in A. Alright, so at the end of the day, if I do that, C is in B and is found in A, you eliminate it. Okay, D is in B and is found in A, you eliminate it. Every other thing else you have in A, you write it down. So A minus B will just be A comma B. I hope you got that right. Okay, so that is the difference of two sets, right? That is the difference of two sets. So from that idea, you understand what the difference of two sets means. So they are, if I have two sets A and B, their difference is simply the element in one that is not found in the other. Now you must take note of something. A minus B is actually, the difference of two sets is not commutative. So A minus B is not equals to B minus A, and the reason is because of their element. I mean, because of, yes, their element. Let's assume that A minus B is actually equals to B minus A. This will only occur if and only if A is equals to B, alright, which will give us an empty set. If and only if A is equals to B. So the only time when the difference of two sets is commutative, this I believe, if you check numbers, if you check my lessons on numbers, where whenever we discuss mastering algebra, basic algebra, you would understand what commutativity means. So the difference of two sets is only commutative when the two sets are said to be equal. And here the difference of two sets is not commutative. Okay, generally this operation difference is not commutative. It's not commutative. All right, so take note of that. Difference of two sets is not commutative. Okay, now let's move on. Now let's begin to define sets in a much more technical way than we have been discussing. Let's see more technical ways to define a set. Look at this. If I say A, if I write this, I'll tell you what each term means. X dot dot, let me say B, Y slash X elements of N 0 less than X less than 5. Okay, or let's say minus 5 less than X less than 5. Okay, and let's say this one, let's say Y, an element of say Z minus 3 less than X less than 1. Okay, now look at these two sets. Let's look at these two sets. This is a full-fledged definition of a set. Remember, we said that a set is the collection of items, bounded collection of items, or collection of items bounded by some set of values. Okay, so it's important that you understand that when you define sets in an advanced level, we must understand that boundaries are put into consideration. Now, what does this set A mean? If I'm going to list or define this set, let's look at each and every line. X, this full colon you have here means such that, okay, so X is such that X is an element of natural numbers. Natural numbers are strictly positive integers, or also call them counting numbers. You should also check the lesson, like I said, on numbers to know what each of these symbols mean. Now you have -5 less than x less than 5. This is an interval that is listing the values of x from -4, -3, -2, just up to 2, 3, up until 4 and then 5. Now, why didn't I mention -5? Why didn't I list -5 and 5 itself? Because this is an open interval. Okay, so we are not going to consider the boundaries. Let's assume I put or equal to. If I do this, less than or equals to, let's assume this was what was there. In that case, I will put then I will include the boundaries -5 and 5, okay, in my listing. All right, so ordinarily these elements that I have here are listed this way, but now they said x, the same x here, must be an element of natural number. So which means that if I want to define A is dependent on this condition. I do not just list this as A. This is not A. I need to look at this condition here. So the condition says that x is such that it must be an element of natural numbers. So once I list all this, I will now look at this again and then consider only the natural numbers. So that is my A will just be 1, 2, 3, 4, 5, because I want strictly positive numbers. So we see the way this set has been defined. Let's look at set B. For set B, we have y such that now either full column or a slash like this, either one of these guys represents such that. Okay, so y is such that y is an element of negative integers. Z represents integers. Okay, yet again, if you want to know about numbers and their symbols, or just want to have an overview of real numbers and understand how numbers work in algebra, you can visit my previous videos to know that. All right, on mastering algebra, there's a playlist there in my YouTube channel. Okay, so now we have y being an element of negative integers, right? Like we did here, you list these guys. This guy means -3, -2. Oops, am I supposed to put -3? No. Okay, because this is an open interval, right? So -2, -1, 0 and 1. But we said we want just negative integers, so I'm going to have -2, -1. All right, so this will be the element of this set. 0 wouldn't be part because it's not a negative integer. 1 wouldn't be part at all because 1 won't even be in this listing because it wasn't closed. Okay, so it's just -2, -1, 0. These are the elements of what we have here. But from this condition, y is said to be an element of negative integers, so which means that I'll just have -2 and -1. So if I'm going to look at the operation of A and B, I can say that A intersection B would give me an empty set. I believe you agree with that. Or I can write it this way, and the cardinality of A intersection B is simply 0. So it's a null set or an empty set. Then if I have if I look for the cardinality of A union B, but I'm asked to find the cardinality of A union B, I must first list what A union B is. So let's see. For me to list A union B, what do you say? Coming together of all the elements you have. So that means you have -2, -1, 1, 2, 3, 4, 5. So these are the elements of it. So that means cardinality will be 1, 2, 3, 4, 5, 6, 7. So n of A union B equals to 7. I hope we're learning. All right. So that is that about that. Now in the next lesson, we'll be talking about something far deeper than all what we've been saying. We'll quickly look at symmetric difference. We'll look at symmetric difference in the next lesson, and we'll also look at a more deeper level of set theory, which involves analyzing the diagrammatic representation of the set. We'll look at the Venn diagrams. We'll look at how you can analyze Venn diagrams All what we have been saying in symbols and letters, how do we put it down in terms of a graphical representation? And also we'll be looking at how we can evaluate some of these things we've said. A union B, look at how we can look at it in terms of its cardinality. Look at the cardinality formulas. Okay, we'll look at what your universal set entails with respect to your operations, and we'll look at how this set actually helps us solve questions in the next lesson. I hope you've learned something. If you found this video very helpful, please do well to share, like, comment in the comment section, and also subscribe to the channel. See you soon.